Okay, today we will look at van der Pol oscillator, that is here. You are familiar with it. We will look at it using harmonic balance. As I have explained, a sine omega t, omega is to be found, it is the time period of the oscillator. The cosine omega t term is not retained because this is an autonomous system. So I can start the clock in such a way that one of those is 0. The sine 2 omega t and the cos 2 omega t I am retaining, but you will see that they are in fact 0. Then I am retaining a sine 3 omega t and a cos 3 omega t. So in this approximation, which I am calling XA, there is one unknown A, one B, one C, one P, one Q, and one omega. That is 6. There are 5 terms here, but remember that the cosine of omega t is implicitly retained. Okay, so 6 terms retained implicitly and 6 unknowns. When I substitute, and I will remind you of course that there is a limit cycle, we have seen that, and so there is a unique periodic solution once we set the cosine omega t to 0. Okay, we expand the approximation into the differential equation VdP here, then we expand and then we do combined trig, and then we pull out the coefficient. So here is, so if I start like that, here is the coefficient of sine omega t, the coefficient of cosine omega t, sine 2 omega t, cosine 2 omega t, sine 3 omega t, cosine 3 omega t. Okay, epsilon is the free parameter that remains. So actually now I have 6 equations involving 7 quantities in which epsilon is my bifurcation parameter. Very good. Then I go to MATLAB, and when I go to MATLAB over here, in this file, x is the input variable, epsilon is the parameter that is being changed. So the global variable alpha that I have discussed, epsilon is now alpha. Here are my 6 input variables, x1 to x6, a, b, c, p, q, omega as discussed. Then over here there are 6 lines, so 1 line, 2 lines, 3 lines, 4 lines, 5 lines, 6 lines. They all end like this with a semicolon after the first line, semicolon after the second line, after the third, fourth, fifth, and a square bracket closing the 6th one with a semicolon to suppress display. Okay, now I come here and I say CLC, get rid of everything. I'm going to solve those harmonic balance equations. I trust you to see that these are just the cut and pasted equations from here. This one, then this one, I don't mean that, this much, then this one, and so on. Okay, now I come here, I go global alpha n big X, so I say alpha equals 0, I say Newton, and now look, I am giving initial guesses. So based on our prior analysis, we know that A equals 2 in the sine omega t term is a good answer, so I'm setting 0 for everything else, and this is omega, not epsilon. This alpha is what epsilon is. So when alpha goes to 0 or epsilon goes to 0, there is the solution where the natural frequency is 1, omega is 1, and the amplitude is 2. So this should satisfy the equation exactly, and it does. Okay, so you see that's the answer, and then I assign that to big X, and then I say alpha equals, and I increase it just a bit, and then I use the same initial condition, and then I assign that also. Now I have 2 points. This is omega, that omega, this is epsilon. The omega would have changed, it would have changed, you know, on a later decimal point. So if I go format long and then I look at big X, then you see the omega has in fact changed. It has changed, but it is small. This 2 has changed a little bit. This B and C, these are the 2 omega t terms. Their coefficients remain 0. The 3 omega t, sine and cosine, they are appearing. Alright. Now I will go again to format short. Then I will go continuation, maybe 60. Okay. Let's see how far we have gone. We have gone to epsilon equals 1.2119. Good enough. That's a fairly large number. Okay. Let us now go to this one, which is the van der Pol equation. I had run this calculation before. That is why I have put epsilon equals 1.2119. And this is just the van der Pol equation. You can look at the code and verify that it is correct. Then what we will do here, this is saved, doesn't matter. What we will do here is we will define OP. We will run the code and just some small initial condition, and then I will plot TQ, and you will see here that the amplitude grows, saturates very rapidly. The red part is x dot and the blue part is x. There is some distortion. It is not purely sinusoidal, but we are approximating x, only the blue part. And so what I will do here is I will now plot only x, and when I look at that, you will see that there is some distortion over here. This is fine. Now I will say A equals, and I will just pull out A equals big X, all rows, last column. That is this one over here. Okay, and you see that the 2 omega t sine and cosine are still 0. Then what I will do here is I will say tau is equal to omega, which is A5 times t. Then I will say x is equal to A of 1 times the sine of tau plus A of 4 times the sine of 3 times tau plus A of 5 times the cosine of 3 times tau. This is my harmonic balance approximation. Okay. Omega is already included. Now we will look at the solution, and what we will look at is this here. This is still a function of t, but x, which is explicitly written in terms of tau. Okay, so t and x. When I plot this, now that's clearly wrong. Why is that wrong? It is wrong because this is A6. Okay, all right. So now you see that there is a reasonable match. In fact, this t can be shifted a bit, right? So I think if I look here, sorry about that delay there, but if I look here, this shift is about from here to here is about 3.5 or something. So let's try that. No, I think I went too far. Let's see. What is the mistake I'm making here? 53.5, 52.5. That's 1.1. Okay, so let's try You see, now you can see that the match is fairly good. The waveform is reasonably matching. The time period is matching. This one over here, this red one, is the periodic solution calculated. So it is, and the blue one is the periodic solution that appears in the numerical solution. Okay, so you have seen an example of harmonic balance applied to the van der Pol equation. This is all I wanted to show you.